Hey, so for lesson 6, we're going to be solving exponential equations. That means it's an equation and it has a variable in an exponent. So it won't be a variable to a power. It won't be like an x squared. We did that back when we did quadratics. These will all have variables in the exponent. So our learning target is to solve exponential equations. Success criteria, can you solve exponential equations? And we're going to go through a few different types or a few different ways of solving these equations. So the first thing to note, if you have an equation, so an equation means that the two sides are equal. If they have the same base, so here it has a 3 and a 3, the bases are the same. If those are the same, if those are equal and these two sides are equal, then that means that their exponents must also be equal. 3 to the 4th would only equal 3 to the 4th. So if this is the case, if the bases are equal, you know the exponents are equal. So this one, there's really nothing to solve. I just kind of wanted to do a really basic one so you could see what was going on. But then we come down to one like this. So here, these are both 2 for a base. So if the bases are equal and the two sides are equal, then the exponents must also be equal. So here we're going to have a little more work now, though. So these two exponents must be equal. 3x equals 5x plus 8. And now we have one where we actually have an equation that we're going to need to solve. So we would subtract 5x from both sides and get negative 2x equals 8. And then divide both sides by negative 2. So we get x equals negative 4. And as you know, the great thing about solving equations is that you can always substitute your answers back in to make sure that it's right, that it worked, that you got the right answer, which I wouldn't do on homework, but on a test maybe. So if I put negative 4 up here, I would get 2 to the negative 12. And if I put negative 4 up here, negative 20 plus 8 is negative 12. So we're good. But that's kind of a basic form. They're not always going to have the same base, right? So here we come over here to B. This one does not have the same base, a 2, and the other is a 16. But sometimes we can rewrite them so that they do. So 2, I can't write 2 as anything smaller to an exponent, right? 2 is as small as it goes. But for the 16, I can write 16. So we can write 16 with a base of 2. 16 is 2 to the 4th power. And that way the base will be 2 and this base is also 2. But when you do that, it already had an exponent there. So this side is 2 to the 2x equals. Now instead of 16, I'm going to write 2 to the 4th because 16 is equivalent to 2 to the 4th. And now both of my bases are a 2. But don't forget you also had another exponent here, which was x plus 2. So when we did properties of exponents a while back, when you have an exponent to another exponent, so power to a power property says that you multiply them. So when we have a power to another power, we multiply those exponents. So 4 times x is 4x, and 4 times 2 is 8. So now we have the same base, 2 and a 2, and if the bases are equal, then the exponents must be equal. So I can set up a new equation just setting those exponents equal to each other. 2x is equal to 4x plus 8. So if I subtract 4x from both sides, negative 2x equals 8. Hey, x equals negative 4 again. X is negative 4. So let's try one more together. Okay, this one, they don't have the same base. They are not a common base. But this one I had a 2, and I could rewrite the other side, the 16, to have a base of 2. So if I look here, the smaller side is 125. If I try to do 125 to a power. So like 125 to the second, that's a huge number. I am not going to get 625. That doesn't work. So for this one, I actually need to rewrite both sides. I need to change the 625 to something, like a number to a power, and the 125, a number to a power. Your key is they both end in a 5, right? The only thing to a power that's going to get you a 5 is a 5. So some of this is going to involve a little bit of kind of trial and error and just testing some things, but try to be a little bit strategic about it. You're not going to do 2 to a power and end up something that ends in a 25. You're not going to do 4 to a power and do something that ends in a 25. So try to be kind of thoughtful. If it's an even number, try 2 and 4. If it's an odd number, you could try 3s and 7s. If it ends in a 5, it's going to be 5. So, and then you're just going to have to guess and check in your calculator because you probably don't know 5 to a power that equals 625 off the top of your heads. But 625, I can rewrite as 5 to the 4th power. And 125, I can rewrite as 5 to the 3rd power. So the key is these bases need to be the same number. When you rewrite them, they have to be in the same base. Sometimes you'll only have to change one of them. Sometimes you're going to have to change both of them. So I'm going to change the 625 into 5 to the 4th. But don't forget, we already had an exponent there, x minus 3. So don't leave that off. Equals, I'm going to rewrite 125. I'm going to change 125 to 5 cubed. But I also already had an exponent there, x minus 4. Okay, so my bases now are both 5. When I have a power to a power, we multiply. So 4 times x is 4x. And 4 times negative 3 is negative 12. On the other side, I have 5 for my base, and then power to a power, we multiply. 3 times x is 3x, and 3 times negative 4 is negative 12. So the bases are equal, 5 and 5. That means that the exponents then must be equal also. If the two sides are equal and the base is already equal, then the only way that happens is if the exponents are also equal. So 4x minus 12 has to equal 3x minus 12. If I add, let's subtract the 3. If I subtract the 3x, I get x minus 12 equals negative 12. And then add x to both sides, I get x is equal to 0. So this try one, that means you take a second and try this one and see if you can do it. See if you can follow along what we did with the last example and try this one for yourself. So you should pause it and then come back to it once you've done that. Okay, so 27 and 9, they are odd. They're fairly small, so you probably would be smart to try a 3. So 27, I can rewrite as 3 to the 3rd. 3 times 3 times 3, 3 times is 27. And then we already had the exponent x plus 5 equals 9, we can change to 3 squared. And then we had the exponent x plus 2. So power to a power, we multiply them, and we get 3 to the 3x plus 15 equals 3 to the power to a power, we multiply 2x plus 4. They have the same bases that are equal, therefore the exponents must also be equal. So 3x plus 15 equals 2x plus 4. And then we're going to solve. So subtract 2x from both sides. X is negative 11. And remember, you can go back, plug them in, use your calculator, and make sure that it actually works, that you actually get the same thing on both sides. Okay? Sometimes that doesn't work. So if you look down at these equations down here, there's not two different sides that both have x's, that both have exponents, I should say. There are not two sides that have variables in the exponent. If that is the case, then you can't do what we did up above. So we need another way to solve those. And this is where all of that logarithm work that you've been working so hard on for the last few weeks, that's where this comes in. So if you can't use the method above, we're going to have to use logarithms to solve. So what we want to do is whatever term has the variable exponent, so the variable is 10 to the 2x, right? That's the term, that's the part that has the exponent. I want to get rid of everything else first. I want to isolate that number with the exponent. So in this case, I need to get rid of the 25. I'm going to divide both sides by, did I say 25? The 75. I'm going to divide both sides by 75. So 300 divided by 75 is 4. Okay, so I get 10 to the 2x equals 4. Once you have that isolated and there are no other numbers on that side, then we're going to rewrite it in log form. You're going to convert this to a logarithm. So we just had the quiz on that, practice rewriting. So we do log. The base of the exponent is the base of the log. Remember, logs equal exponents. So logs equal exponents. What was the exponent? The exponent was the 2x, which means that what goes here, the only thing left is a 4. This just goes in your calculator. So you're going to use your calculator to evaluate this. You'll get a decimal. It's not cute. That is okay, right? We are like past the days where everything comes out to be all nice and pretty. So log of 4 using your calculator is a decimal, 0. Watch to see what delta tells you to round to. That's super important. And don't round early because your answers will be a little bit off. Equals 2x. And then you just have an equation with no exponents, no logs that you would solve like any other algebraic equation by dividing both sides by 2. So x equals 0.301. I'm going to round to the nearest thousandth. That's usually far enough for delta. Okay, so step 1, you might want to write these in your notes off to the side because I didn't do this. Step 1, isolate the base with the exponent. Step 2 is to convert it into log form. And step 3 is to solve the algebraic equation. Okay, so here's the term or the base with the exponent. I want to isolate that. I want to get rid of the 8. So I'm going to move the 8 to the other side. I'm going to add 8 to both sides. You can't divide this by 17 because it's an exponent. These aren't being multiplied. So step 1, we isolated the term with the exponent. Step 2, convert it to a log. So log, the base of the exponent is the base of our log, equals, logs equal exponents. So the exponent always goes on the other side, 6a. And then what do we have left to fill in this hole right here? The only number that we have left that we didn't use is 48. So hopefully you remember how to do the change of base formula. This is why we practice that. The change of base formula, we do log of 48 divided by log of the base. So divided by log of 17. And we're going to get an ugly decimal, which is what's supposed to happen. 3.6636. And then the last step is to solve the algebraic equation. So we're going to divide both sides by 6 and a is equal to 0.238. For notes, I'm just going to round to the thousandth. For delta, do what he tells you to. Okay, if you're feeling good, go ahead and try these two. Pause me and try these two. If not, then follow along with. We're going to do two more that are similar. They just a little bit different in terms of like isolating it first or solving afterwards. Okay, so in this one, this whole thing has the exponent. The exponent is x over 5 minus 4. So I need to move the 1 first. So I'm going to subtract 1 from both sides, and I get 1.1 equals 1.01 to the x over 5 minus 4. Okay, so step 1, isolate that thing that has the exponent. Step 2 is to rewrite it, convert it to a logarithm. So log the base, the number that has the power is the base of the log, 1.01. Logs equal exponents. So the exponent is on the other side of the equal sign. And then that leaves the 1.1 right here. So log of 1.1, remember log of the big number divided by log of the base. So one thing to do is, I don't retype this into my calculator, right? You have this in your calculator because you just did it. Like that's how you got it. So just don't clear it and then use that to solve. So now I'm going to add 4 and hit equals, because adding 4 would be my next step. You can write it here if you want. I actually don't even do that. I just kind of keep doing step by step. But so I added 4 to both sides. I'm keeping that in the calculator. I'm not going to clear it out and retype it. I'm just leaving it there. And then the next step would be to multiply by 5. So x equals 67.893. Okay. If you haven't already, go do that now. Go pause it and try this one now. Okay. So the last one of these, when we say isolate the part with the exponent, notice up here, the 75 was not part of it. 75 was being multiplied in front. 75 wasn't like in parentheses that had an exponent. So when we look at this one, the part with the exponent is just the 0.915, not the 3,490. So I'm going to add 109 to both sides first. Equals 170. Then I'm going to divide both sides by 3490. I'm still on step 1. Step 1 is to isolate that number with the radical. .0487. Okay, so we've done step 1. We isolated the term with the radical. Next step is to convert it to a log. So log base 0.915. It equals the exponent. So the x minus 2, the exponent goes after the equal sign, which means that this whole thing goes right here, 0.0487. So when you put it in the calculator, this number goes first, log of this number, close your parentheses, don't forget to close your parentheses, divided by log of the base. And then step 3 is to complete, finish solving the algebra. So we want to solve for x, we have to add 2 to both sides. So x equals 34.020 if I'm going to the nearest thousandth. We have one more problem, and that's just to show you an application problem, who the heck would actually want to do this, right? Why do we want to use logarithms? Why do we care about any of this? Remember that in the very first part of this 3-part unit, we were working with exponential functions. So we worked a lot with interest rate problems. So we're going to go back to revisit that for a second, and I'll show you how this applies to it. So it says a person invests $10,000 into a bank account. The bank pays 5.5% compounded monthly. To the nearest tenth of a year, how long must they leave the money in the bank to have $27,400? So as a little reminder, this was the equation we used. A was your final amount, so that's going to be the $27,400. P was your principal. That means how much did you start with? How much did you initially invest? That was $10,000. R is your rate, so 5.5%, but we need to write it as a decimal, which is 0.055. And N is the number of times per year they compound your interest. So if they're giving you interest monthly, if they're compounding it monthly, there are 12 months in a year. So N is 12. And T is the number of years. So we are trying to solve for T. We're trying to find the number of years. So when in doubt, plug in all the stuff you know, and then maybe something will come to you. 27,400 equals 10,000. 1. And then the exponent is going to be 12 times t, so 12t here. I am going to do this as a decimal first. Did I do enough zeros? I missed a zero here, didn't I? 27,400. Nope. Then I'm going to divide both sides by 10,000. Oops, 2.74, sorry. Missed a decimal there. 2.74 equals that decimal to my exponent. Okay, so I've done step 1. That all was just step 1, which is to get the number with the exponent by itself. Step 2 is, so anyway, let me go back for a second. This is why we care, because we had a variable in the exponent. So sure, we could does it take 2 years? Does it take 5 years? There was a problem in one of the very first assignments where you were supposed to use Desmos and graph it to figure out when it would equal that. The graphs end up huge. It's a pain in the butt. It's not very accurate. So this is how we would solve for a variable in the exponent like this. How do we know what the time needs to be? How long do I need to leave it in there? When do I need to start saving? So step 1 is to isolate that. Step 2 is to change it to a log. The numbers are gross. That is completely okay. You have your calculator. They're not pretty in real life. So there's the base. Logs equal exponents. So the 12t goes on the other side of the equal sign, which leaves the 2.74 here. So I'm going to evaluate this on my calculator. Log of 2.74 divided by log of that 1 point decimal. Again, you don't want to be using your phone, right? Phones are the worst calculators. Remember I said that? And then your last step, step 3, is to solve the algebraic equation. So we're going to divide by 12. Again, don't retype this in your calculator. You should already have the big calculator or the big long decimal in your calculator. And I think it said to the nearest tenth, which would be 18.4 years. T is time, the number of years we're solving for. So you would have to leave that money in the account for almost 18 and a half years to have $27,000.